Hello and welcome to this talk on how Pureinsights built a proof of concept for the Publications Office of the European Union by adding dense vector support to their existing large-scale Elasticsearch instance. The intention is to allow European citizens to ask natural language queries of the information, very much Google style. My name is Phil Lewis and I'm the CTO of Pureinsights, a Washington DC based company that focuses on adding Google-like features to open source search engines like Elasticsearch. I'm based in the UK and I've been working in the search industry at companies like Convera, Indeka, Search Technologies and Accenture for the last 30 years or so. Okay, let's get right into it. Answering questions with a search engine goes by a number of names. The industry has over the years called these things semantic search, cognitive search, and more recently vector search because of the underlying technology that it's using. Today I'm going to really be calling it semantic search for the remainder of this presentation. But the key thing that is important is that all of these capabilities tend to use very similar technologies. So that'll be natural language processing to do semantic understanding, possibly some machine learning there, maybe some AI-based models to help the system understand not only the query intent but the original content as well, and potentially a knowledge graph. This is one thing that Google is injecting into the search engine results quite a lot these days. By adding a knowledge graph to the system, you can get very authoritative answers from that data set. And all of these technologies working hand in hand really comprise this idea of semantic search, cognitive search, or vector search. And if you've been in the industry for any length of time, then you'll very quickly realize that these terminologies have been used for quite some time. But we've never really been able to deliver on the promise of this up until relatively recently. So why now? Well, it's really to do to some technologies coming together all at the same time. If you look at this chart, over time, it's kind of showing you the efficiency and the effectiveness of technologies in the space. And what we're finding is up there in the top right-hand corner is we're starting to see a number of technologies come together at the same time, which is almost a serendipitous moment. We can start to use these technologies for the first time hand in hand to enable us to do this semantic search capability that we've never really been able to do in the past. So this includes things like neural AI models. This has really been a very, very big leap in the capabilities of natural language understanding. The availability of almost infinite cloud compute capability to end users to, number one, build these models, and number two, to execute these capabilities as quickly as possible, sub-second. The access ability to very large-scale data sets, which gives us that base understanding, that base learning that we can use to understand information as we process it. And lastly, the very fact that machine learning algorithms are now out of universities and into industry has really helped us to better process content in such a way that we can provide these kinds of capabilities. So this combination of technologies has really helped us to advance the search capability at the European Union Publications Office. So just talk a little bit about those guys. They're based in Luxembourg. They have over 600 staff, and essentially their mission is to provide all of the wealth of information that the European Union generates on a day-by-day basis in a centralized location. And this would include things like all European Union laws, all the publications associated with those laws, any open data assets that they may have, and allow European citizens to get access to those data assets and then kind of munge the data, process that data to discover the secrets, discover new insights from that data as they see fit. But all the way through even to procurement notices. The European Union fund a lot of research around the European Union very regularly, and those procurement notices are all officially held by these systems, and they provide a single search experience that essentially enables any European Union citizen to get access to all of this data from this centralized data set. On the left here you can see their Elasticsearch instance and how they render the information to the end user, but on the back end they're actually using Oracle RDF as the triple store, and that then is being rendered and mapped into an Elasticsearch index. So chunks of text are coming through, all the metadata is coming through, everything that you need in order to provide this keyword search capability for the European citizens. And of course, being the European Union, nothing is quite as simple as it should be. But here we have one rendition of a document on the right-hand side, and you can see what that document looks like. But on the left-hand side, you can see there are multiple renditions to the same document. So every document has to be translated into as many of the European languages as possible. It's about 24 European languages in total. And there are multiple renditions of each of those document objects. So whilst this one document exists in kind of a logical form on the right-hand side here, in physical form it may exist in all of this very expanded set of content types that any European Union citizen can download. But the Publications Office is starting to see a trend which is also seen by Google, and now we believe that approximately 12% of all Google queries on google.com are now fully formed questions, and you've probably used google.com to ask and answer questions very recently. It's something that they've started doing maybe 2 or 3 years ago in earnest. And of course, the Publications Office are also now starting to see a similar trend. So their current keyword-based search mechanism really needs to be extended to allow these types of questions and answers to be provided by Elasticsearch behind the scenes. And because of our long-standing relationship with the Publications Office, working for them for many, many years, we got the following challenge, which is just make it work like Google. And I think you'll see a lot of resonance with that sentiment in all your search projects coming up. So just before we get into it and show you the demonstration of the technology that we built, I just wanted to set the scene a little bit about questions and answers in Google, and then we'll address that point within Elasticsearch specifically. So here we're in Google, and I'm just going to execute a query, and this query is asking for the European Union Publications main mission, just as we saw a little bit earlier, and we got an answer provided at the top of the result set. If you look at this answer, it's actually what Google call a featured snippet. The industry is really starting to call these extractive answers. Google is still calling these things featured snippets, and why not? They invented it. And it provides the answer directly at the head of the result set. So keep an eye out for this little signal here that tells you that this is a featured snippet or an extractive answer which has been returned by Google. I'm going to ask it a different question. So where is the European Union Publications Office essentially located? And again, it's bringing us an answer. It's highlighting the answer within situ, within the document body itself. And this is also a featured snippet. Okay, so for these two questions, Google has deployed its featured snippet capability, which is all about NLU, natural language understanding, vector search, and things like Google BERT helping out behind the scenes. Now, if I ask it this question, when was the European Union Publications Office founded, we get a slightly different response. If you notice, there's no featured snippet information returned here. We get the answer. It doesn't quite look the same as the answer that we had from the featured snippets, and that's because this is coming from directly from Google's knowledge graph. So this is a knowledge graph answer. So sometimes it's confident enough to answer the question directly from its own knowledge graph, and this time we get that answer presented like this. Now, the way you tell that this is a knowledge graph answer is we have a semantic triple up here, right? So we have the node of interest within the knowledge graph, we have the attribute of interest, and then we have the answer that's attached to that attribute. Okay, so that's how you tell whether a question has been answered by the knowledge graph or whether the answer has come from the AI, Google BERT and other models using its featured snippets capability. But I want to go a little bit deeper. So I'm going to ask it a much more, and again we're asking Google here, ask it a much more deeper question. So here we know and we understand that the European Union Publications Office are holding a lot of European Union law information, And here we're asking it about a specific decision that was made on a legal case. And we just want to know what the date is. So in this case, the system has gone quite deep into the European Union dataset, and it's found this object. And this object is essentially saying that the date of the judgment of that specific case was the 20th of October 1993. And here, because now we understand the tricks, it's all about featured snippets. So this data has been snipped out of the data set, actually quite deep within the European Union Publications Office data set by Google. And this is exactly the kind of capability that the European Union Publications Office wanted to add to their Elasticsearch capability. So if we take this exact same query and copy that into the Elasticsearch based questions and answer system, then we get pretty much exactly the same query. We are extracting the answer just like we did in Google, and we're also extracting and highlighting that answer within the context of the query itself. If I ask it just a couple more questions, just so you can see the kind of capability that we have here. What are the ethylene capacity rates in Western Europe? Then again, the clues are in the question, and the question is trying to find out some kind of capacity rate within the system, and here we've got capacity and rates. If I do a question like this, again against the Elasticsearch AI enhanced system, then we get a response. This is quite an interesting response because the question itself is talking about stopping manufacturing, whereas the text is talking about production until. The system is talking about ethylene byproducts, and this document is talking about ethylene derivatives, and yet it still successfully brings out the answer, which is when that was actually stopped being produced. And lastly, if I do a query for something like this, which country submitted an updated version of the MPAA in July 2001, then again we are extracting the answer directly from the content, simply because this was talking about the acquisition of an MPAA in July 2001, and that answer is correct. So how did we do that? What technologies did we use behind the scenes, along with Elasticsearch, of course, to enable us to do that kind of capability for these guys? What we did is we used our own Pureinsights discovery platform, which just encompasses a bunch of predominantly open source technologies into a single framework to enable us to rapidly iterate on this capability. You don't need to use the Pureinsights discovery platform for this, of course, but it just makes it a little bit easier. And what we did is we hooked up to their document store. And remember, their document store was essentially Oracle RDF. And we extracted all of the main components of the documentation that we thought were useful for answering questions over. And we configured a series of pipelines to process that data. And one of the big things that we needed to do with the data is any significant documents over kind of 512 tokens there or thereabouts, so 512 words there or thereabouts, we'd have to chunk that document up into logical chunks, mainly paragraphs, sometimes sentences. And the main reason for that, of course, is that the attention span of these NLP models is, at the moment, relatively small. So they can process chunks of text up to about 500 tokens in size. Once you get beyond the 500 tokens in size, they either get truncated or they lose detail. They lose focus, essentially, on the text itself, and you can't be confident about whether it's got all of the nuances of that chunk of text itself. So putting whole documents into dense vectors using current models, and I think things are changing, but at the moment with current models you really need to split those whole documents up into logical chunks. So that's one of the key things that we did here. And then we used, of course, transformer models based on Hugging Face framework. We used Google BERT, and slightly different variants of Google BERT to provide this capability. They were just loaded up into a Hugging Face framework and then executed on GPU so that we can very, very quickly generate those vectors. And then we used Elasticsearch to store those vectors for each chunk. So if you think about it, one document in might mean several chunks out. In fact, it could be 50, 60 chunks out for one document coming in, depending on how large that document actually is. We store all of those chunks in Elasticsearch as individual records, and we kind of join them together again when we need to by a group by function later on down the line. So we store those vectors inside of Elasticsearch, and they're kind of ready to be searched at that point. When the query comes in, of course, then we also have to vectorize. We can't use keyword queries against vectors, so we have to vectorize the query as well, and we use exactly the same service to do that. It provides a normalized vector between the documentation side and also the query side. And then we compute either a cosine similarity or a dot product similarity between those, the query essentially, and the document chunks. And then, of course, what that does is it will generate a set of candidate answers. Not necessarily the perfect answer in hit position 1, because now we're at the neural kind of level and it just spits out a score. And we have to do a little bit of work to understand whether we've got the right answer or not. So these set of candidate answers, and this could be a window of, let's say, 10 candidate answers or 25 candidate answers. What we then do is we request answers from a Q&A model, right, using a fine-tuned variant of DistillBERT, which can answer questions. So we request the answer from DistillBERT, which again is running inside a Hugging Face, and then that enables us to understand, out of these top 10 chunks, do we get a consistent answer out of them? Do we get conflicting answers out of them? What's the score profile look like for the candidates? And we do a lot of analysis on that data set in order for us to compute the answer. So we effectively compute, using an algorithm, what we think, whether we're confident, essentially, about that score or not. And that uses a lot of just background information. It might use even things like document authority models, author models, and various other pieces of information to say, okay, if we get an answer from this author, then we are more confident than if we get an answer from this other author. Or if we've got an answer from a highly authoritative piece of content, highly trusted, highly used, highly cited piece of content, then we can be more confident about that answer than if we get the answer from a temp file. And I realize that's a silly scenario, but you can imagine potentially getting an answer from a very unauthoritative document, in which case you might not want to produce that answer. And then just stepping up one level, just to understand the complete picture from a very, very high level. On the left-hand side, we have the data sets that we are hooking up to. We use data repository connectors to do that. That extracts documents, containers, security ACLs if there happens to be any there, and additional metadata. We then stage that data in a staging repository. This could be Elasticsearch itself, of course, or it could be other NoSQL style databases. And then we have these content processing pipelines. And if you remember, this is where we chunk text and do all sorts of interesting analysis on the text itself. We push that data out as part of the content processing pipelines into several AI services. That includes this open source Spacey NLP capability. We also use Yake, which is another open source keyword extraction capability. Obviously we use Google BERT, which is now open sourced, of course, and we're also starting to look at a new model called Mini LM L6, along with DistillBERT, to help us answer those questions. All three of these are running inside the Hugging Face component within our framework here. And then once we've manipulated that data and enhanced that data by adding vectors to it, then we store those vectors inside the search engine. Now, PDP also has the ability to do what Google is doing in terms of knowledge graph answers. We didn't really talk about that in depth today as part of the project in question because we didn't want to lose focus of extractive answers. But essentially, we can also add knowledge graph answers to these capabilities as well. For knowledge graph, we use Neo4j, which is one of the industry-leading open source knowledge graph systems that's out there. And the only difference, if you like, instead of putting vectors into Neo4j, we put semantic triples. And we now understand a little bit more about semantic triples from earlier in this presentation. And then we've got a query API, and this is where the magic really happens, or the intelligence really happens, because users' queries coming in from the outside world need to be understood by the query NLP API. Sometimes that may manifest as just a search to a search engine because it's just a set of keywords that the user has executed. It may be that the user has put a fully formed question into the system, and then we need to go down a different path and possibly add a vector search to the dense vectors capability within Elasticsearch. It may be that we can spot entities within the query. Most notably, we're looking for semantic triples here, right? So we're looking for the entity of interest and we're looking for the attribute of interest, and then maybe we can answer that directly from the knowledge graph. But for extractive answers, we typically always go to the search engine for that capability. And so with that, I'd just like to thank you for attending this talk today on what I hope you agree is a very interesting subject. You can reach out to me at phillewis@pureinsights.com and feel free to visit our website to understand a little bit more about what we do. Thank you very much for your time.